Hi, everyone. Welcome to our special astronomy lecture this evening. Tonight's collaborative effort is between the Southern Vermont Astronomy Group, or SEVERA, the Dublin School's Perkin Observatory, and Middleman Observatory at Middlebury College. For SEVERA, this is our monthly meeting. For the Perkin Observatory, this is one of our aperiodic astronomy lectures. And for the Middleman Observatory, this is the fifth installment of our Middleman Astronomy lecture series. We're very fortunate to continue this in a virtual form tonight in order to extend the accessibility and the reach of this talk. In addition to members of SEVERA and students at Dublin, we have other astronomy and space curious individuals and amateur astronomers from New England and beyond, including other high school students, college students from the region, etc. In addition, we have numerous Middlebury students, community members, faculty and staff, and alumni as well. So it's really nice to see such a diverse audience. My name is Jonathan Kemp. I'm with the Middleman Observatory under the dark skies here in the Champlain Valley of central Vermont. After a few quick additional notes, I will then pass it off to Pat Porch of SEVERA to introduce tonight's speaker. At the end of the evening, Eric Schmidt of Perkin Observatory will handle questions and answers from the audience. So I'd like to briefly mention some tech notes and rules of the road. This lecture will be recorded, but attendees do not have video enabled and will only potentially have audio enabled for questions at the end, which are encouraged. If you have technical questions, please use the chat function to connect with our panelists who are hosting the event. If you have astronomy or other subject matter questions for the speaker, please use the Q&A function. You can also upvote questions or comments from others in the Q&A area if you'd also like to see them addressed after the lecture or even during the lecture. We may interject and have a few of those posed to our speaker tonight as well during the course of the presentation. You may ask a question verbally at the end of the lecture using the raise hand capability within the participants window, and we'll give some priority to those as well. The chat, the Q&A, and the participants functionality should all appear on the edge of your webinar window. While we are very happy to welcome students of all ages, minors and other younger students should certainly seek permission of a parent or guardian before participating in this evening's lecture. Lastly, please remember to share respectfully and with civility as we begin tonight's talk as a community. So with that said, let me go ahead and turn this over to Pat Porch of SEVERA.
Thank you, Jonathan. Welcome everybody to our July public presentation. Today and tonight is all about galaxies, and I'd like to say we planned it this way, but obviously we didn't. That our presentation tonight on galaxies goes along with Webb's presentation on galaxies this morning, and I hope you got a chance to see some of those awesome pictures that they had. I'd like to introduce our speaker, Hugh Crowl. He's a faculty member in Physics and Astronomy at the Bennington College. He's an astronomer with an interest in the evolution of galaxies, and that's what he's going to talk to us tonight. Welcome, Hugh. It's all yours.
Thanks very much. So really happy to be with you tonight. Happy to be here. I'm gonna share my screen, and let's see if we can get that working. Just make sure. Okay, hold on. Let me just get things organized. Okay, that's okay. So that'll work like that, and. Okay, I think this should work. I'm gonna talk to you tonight a little bit about how galaxies lose their gas, and as Pat was saying, the timing is very appropriate because today there were really 5 really interesting results from the James Webb Space Telescope, the first images that we've seen from the telescope other than the calibration images. And I'm really looking forward to talking to you about galaxies and what we've learned about galaxies using techniques other than Webb, and hopefully what Webb can teach us. This is a talk in general about galaxies. Galaxies and galaxies are sometimes a little bit hard to define, even for professional astronomers, how you define what a galaxy is. We've seen pictures, and you'll see pictures like I have shown here of galaxies, which tell you a little bit about sort of what a galaxy is. But I think it's useful to maybe start the talk with defining how we define a galaxy. And so for this, I've gone to the source of all knowledge, Wikipedia, and looked this up. And this is, I think, a really nice, actually pretty good description of what we think galaxies are, what we know about galaxies, and what we see galaxies as. So a galaxy is a massive, big, it has mass, gravitationally bound, it's held together by gravity, system that consists of stars, an interstellar medium. So interstellar meaning between stars, medium meaning stuff, an interstellar medium of gas and dust, and also galaxies have an unknown type of dark matter. And so galaxies typically contain somewhere between 10 million and 1 trillion stars. That's a big range. And they're all orbit this common center of gravity. They can also have multiple star clusters and star systems, as well as various types of clouds that throughout. Let me. So there's a technical question about the presentation. Can we make if the slide can be made bigger? I'm not sure if that can be done, but I don't know if there was some way to do that. If there's a way to do that, or maybe that can be done individually.
I can comment briefly there. So most of this can be controlled on the user end. In the upper right-hand corner, you have a view option. You can go side-by-side gallery, side-by-side speaker, or standard. Perfect. And that should allow the individual viewers to control the presentation as optimal on their end.
Right, my face is much less interesting than the images. So good, excellent, good. All right, perfect. So this is a picture of galaxy. One of the problems with Wikipedia is I've shown this slide a lot in talks I've given, even to professional astronomers, because I think it's sometimes hard to define what a galaxy is. And I went back to Wikipedia to make sure it was still the same, and it actually is. One of the problems with Wikipedia is that it's community based. And so now it's like way too long. This is like one of the fundamental problems with Wikipedia. It was a really nice description. So I'm going to go back to the one that when I first looked this up, almost 12 years ago now, and just say that this is sort of a really nice sort of compact idea of what a galaxy is. As I said, it's surprisingly hard to define exactly what a galaxy is, because there sort of are things that are on sort of the low end of galaxies or the big end of star clusters. Anyway, we won't get into that tonight. But let's look at some pictures of galaxies. And this is up until this morning, I had a picture of the Hubble Ultra Deep Field to show a bunch of pictures of galaxies. But I mean, how could I resist showing this wonderful field from James Webb, just released last night? This is the SMACS 0723 field, which is known for a very strong gravitational lens. This is one of the things that can happen in galaxy clusters. The galaxy clusters can bend light, and you can look at really distant galaxies. And one of the things that you can do if you want to understand how galaxies change, if you want to understand how galaxies evolve with time, one of the things you can do is you can look at galaxies that are really far away. By looking at galaxies that are really far away, you're seeing light that left those galaxies millions or more often billions of years ago, and you can actually see them. And so this is this amazing field. I'm just going to show a close-up on this because a few close-ups, because I think just looking at the whole field doesn't really do it justice. If you look closely, there are one of these things, these beautiful like bent images of galaxies. These are warped as if it's going through a lens, because that's what it is, a gravitational lens. Beautifully warped galaxies. But even if just not paying attention to those, if you look closely at all these images, you can just spend, I think, hours looking at all these images. There are lots and lots and lots of different types of galaxies in this image. There's galaxies that look like this, these little red things. There are galaxies that look like this, round and elliptical, called elliptical galaxies. There are galaxies with spiral structure, really beautiful spiral structure. And there's also another one. There's another one here. You can do also, again, I could spend a long time looking at this. Let's look at another part of the field with many more other different types of galaxies. You see these sort of gravitational arcs, which is sort of a curve here. But also these sort of just, little spiral arms coming off of this one. This is like an edge-on galaxy. This is when I teach astronomy. I have my students spend lots and lots of time looking at images, because I think looking at images, you can really sort of learn a lot about the different kinds of galaxies. Here's a really nice one, a beautiful sort of spiral galaxy. And so one of the ways that you can study how galaxies have changed over time is to look at galaxies that are really far away, so you see them as they existed at an earlier time, and look at galaxies that are close and compare them. And that's what some people do. Some people look at galaxies over a wide range. There are some downsides, though. It's observationally expensive. Even with Webb, you have to, it takes a long time to get good images of distant galaxies, and you lack detail. And so there really is an advantage to studying galaxies that are relatively nearby. And so that's a lot of what my work does. I am amazed at these images. I look closely at these images, but I'm more interested in the galaxies where we can learn a lot of things about them. And so I wanted to show you. I'm just going to show a few pictures of a few galaxies. Before I do, though, I see a question that this idea that Wikipedia refers to an unknown type of dark matter in galaxies, and that is true. And I'll just say that it does appear that there is dark matter. It doesn't necessarily imply that there are multiple kinds. It just implies that we don't really know what dark matter is yet. We have some ideas, but it's not well defined. There's vast numbers of astronomers and physicists trying to figure this out. We know some stuff about it, but we don't really know what it is, which is interesting and exciting to not know stuff. Anyway, let me show you some pictures of some relatively nearby galaxies. And one of the things that we see when we look at relatively nearby galaxies is we can see a lot more detail. So these are images. Many of these are taken with Hubble. Some of them are taken from the ground. Some of them are taken by many different surveys. And one of the things that I just want to draw your attention to is that galaxies, many of the pictures of galaxies we see that look sort of like the canonical galaxy images are galaxies that are so-called field galaxies, or rather galaxies that don't have a lot of other things around them. And on the left-hand side, that's kind of what you see here. You see sort of three different galaxies. I've chosen those specifically because they all look somewhat different. You have a galaxy, a spiral galaxy, a galaxy with beautiful sort of spiral structure and dust and stars and star formation, really sort of a beautiful image up top. You look at the next one down. This is an elliptical galaxy. This is it's in the center, and sort of the light spreads diffusely out from the center. And there's some differences here. This is another disk galaxy, but it's a disk galaxy that doesn't have any star formation. It doesn't have any young stars. It also, not coincidentally, does not have any gas or dust, or at least not very much gas or dust. And that's one of the things that we'll talk about. We'll talk about in a little while about galaxies that maybe had gas at one point, but have since lost their gas. So this is a so-called lenticular galaxy, an S0 galaxy. This is called an elliptical galaxy, and this is a spiral galaxy. When you go to places where you have galaxies near each other, galaxies in dense environments, you end up with galaxies that are often transformed by that dense environment. So I'm just showing a few galaxies here, and these galaxies look very different and in some ways more exciting. I'll just point out, because I said I was going to show three pictures of JWST. This upper right image is this amazing image of Stephan's quintet, which was released just this morning from the James Webb, the first James Webb images. And this is a well-known interacting galaxy system, galaxies that are crashing together. And you just see sort of, the light pulled out here, and what Webb is really showing is a lot of dust as well being pulled out. But you can see that also in optical images. This image right here showing galaxies that are merging together, galaxies that are crashing together. This is a galaxy that's having its gas pulled out of it, which we'll talk about that in some more detail in a moment. But these are galaxies that have sort of, one of the things that sort of is interesting about studying galaxies in more dense environments is that is where a lot of the action is. If we want to understand how galaxies change, we want to look in the places where they're changing. And we know, both from looking at images of clusters, but also from simulations of galaxies, that the places where there are a lot of galaxies close together is a place where a lot of change happens. I'm just going to show briefly this. This is a simulation, a hydrodynamic simulation from the Illustras TNG project that shows galaxy evolution over time. So this is showing these are two big masses of material that are crashing together. And as you can see, so this is just a simulation, but it's showing a simulation over billions of years. What can happen over billions of years? And simulations are really great because you can watch them over time. You can watch them as it evolves. But what you'll see is as these galaxies crash together, they're really fundamentally changing. And so simulations are interesting descriptions, but we want to make sure that those match up with reality. And so what we do is we study galaxies in these dense environments. And the dense environment that I am most interested in is the Virgo cluster. The Virgo cluster is the nearest big cluster of galaxies to us. And there's a huge variety of galaxies here. This is a beautiful image taken by an amateur astronomer that shows sort of a really beautiful wide field image of Virgo. And if you look over this image, you will see sort of all sorts of amazing galaxies that are crashing together. There's elliptical galaxies, like I've said before. There are spiral galaxies here. There's another spiral galaxy here. There's another elliptical galaxy. But there's also galaxies that are very disrupted by their environment. And one of the things that can happen in galaxy clusters in particular is all of this disruption can pull gas out of galaxies. And when that gas gets pulled out of galaxies and when it gets stirred up in a galaxy cluster, it heats up, it gets really hot. And in fact, in a lot of galaxy clusters, most galaxy clusters, if you look at them in the right way, you see this hot gas, this 1,000,000-degree gas that fills clusters. And you can't really see in the optical, it doesn't emit light very well in the optical, but if you look in the X-ray, you can see this 1,000,000-degree gas. And so I'm going to just superpose over this image an X-ray image. And if you look at sort of where the X-ray emission is, you see that it's really centered around the center. And so this is tracing this 1,000,000-degree gas that completely fills the clusters like Virgo and lots of other galaxy clusters. And while there's lots of different ways that galaxies can be transformed by their environment, one of the things that can happen is as these galaxies fall into the cluster, the gas is pushed out of the galaxies. They experience a wind. It's not sort of so unlike if you're driving down the highway on I'll say a still day, you're driving down the highway and you stick your hand out the window, you feel the air pushing on your hand. It pushes your hand back. And you don't have the air doesn't have to be moving, but if you're moving through the air, you feel what appears to be a wind, a pressure on your hand. The same thing happens to these galaxies. As they fall into Virgo, they experience a wind, a pressure, what's called a ram pressure. And as they fall into Virgo, you can actually see this ram pressure pushes the gas out of the galaxies. There's another great sort of visualization, simulation of this. This is, again, a movie, a simulation showing the galaxy moving. You don't see the intercluster medium, but this 1,000,000-degree gas. And as it moves through the 1,000,000-degree gas, it pushes gas out of the galaxies. The stars mostly stay put because the stars are really dense and tight. But you see this gas that's leaving the galaxy. It's getting pushed out of the galaxy. And so this is a visualization, but it's backed up by observations. We actually can see this happening. And so here are images of 3 galaxies in the Virgo cluster. These are galaxies that are all falling into the Virgo cluster right now. The grayscale image, the picture, is a red optical image. So it's an image taken with an optical telescope. The contours show where the neutral hydrogen gas is, what astronomers call H1. And what you see, really convincingly, at least in the bottom one and the one on the right, is gas being pushed out of the galaxies. This gas is, as these galaxies fall into Virgo, this gas is being pushed out of the galaxies, and you're effectively removing gas from the galaxies. You can see this in the H1 imaging, the neutral hydrogen imaging, but you can also see it in optical images. So here are optical images. The top 2 are from Hubble. The bottom one is a ground-based image. You can see these same three galaxies where you can actually see the gas being pushed out. And so I'm going to just take you through this. You're not so much seeing the gas, but you're seeing dust, which largely traces the gas. Gas and dust are all sort of get pushed out together. And so in these images, you can see, so for example, in this top one, you have, this is NGC 4402, you have dust that's being it makes this sort of arc shape. This arc shape is indicative of it's experiencing a pressure. And the material here is getting pushed out. You can see like clouds up here. If you look carefully, maybe you can see clouds even up above it. Clouds of dust that have been pushed out by this wind, this pressure as this thing goes. You also have little star-forming regions. Here's a star-forming region here where the dust is actually pushed away. And so this is cool because it's giving us a direction of the dust. This is another one, same idea. The dust is, the stars are mostly here. The stars are mostly sort of horizontal, but the dust is bowed upwards as it experiences this wind that pushes the gas up. This one is the opposite direction. It's actually the dust. It's a little bit harder to see, but the dust is down here, is being pushed down out of it, and there's this cool sort of pillar of dust that's left behind, which is sort of an interesting picture. And so this is really cool. We actually see galaxies as they are experiencing pressure, as they're being stripped of their gas by this 1,000,000-degree cluster gas that fills the cluster. And we can. This is cool, but it doesn't last forever, and it also doesn't exist in every other galaxy. And so there's sort of two things here, two questions. What is the effect of removing gas from these galaxies, and how can we maybe study this in a larger group of galaxies? And so the first question leads me to probably the most shameless use of a web image for tonight, which is this beautiful image of a star forming region. This is NGC 3324 in the Carina Nebula. And this is just amazing. So this is a stellar nursery, a place where new stars are being born. And what do you see? You see dust, because dust and gas are needed to form stars. And so if you're able to effectively remove that dust and gas, you're able to halt star formation. And this is both an answer to the first question I asked, which is, what is the effect of removing the gas and dust? But it is also a hint into how we can go further in studying larger galaxies and understanding sort of the larger effect of this on galaxies. So I'll pause for a moment because I know I talk fast, and I want to see if there's any questions at this point before I start talking about the effect that losing gas and interstellar medium has on these galaxies. Are there any questions? Yes, Margot.
Hi there. So you're going to talk about the effect that it has on the galaxies, but my question was, what happens to the gas once it's left the galaxies?
Yeah, that's a great question. Lots of cool stuff. One thing that can happen, and let me see if I can get this in the image. One thing that can happen is, do you see these little blue dots up here, sort of blue dots up above here? These are, we think, little star clusters that have formed in the gas as it's been stripped. And so one thing that can happen is, as you pull this gas out, you get little bursts of star formation happening, and you have these floating around the cluster. I mean, can you imagine? It would be amazing to be in a planet around one of these stars, because you would be a complete, you'd be completely isolated in, you wouldn't have many stars around you. You just have your little cluster of stars, and you'd just be sort of alone in this cluster, although lots more galaxies in your sky, which would be pretty cool. So that's one thing that can happen. If the gas can heat up enough, it probably contributes to the intracluster medium, this hot 1,000,000-degree gas that pervades the cluster. So if it can cool and condense and make stars, that's one thing that can happen to it. But probably what happens to most of it is that it gets mixed in with the hot 1,000,000-degree cluster gas and continues to heat up. So yeah, thanks for that. I have at least, I'm trying to figure out I'm not sure how to call on people. Like I said, I have at least two people with their hands up. Oh, I think I can do this. Hold on. So I'm going to try Roderick. I'm going to click on the allow to talk button and see if that works. Yeah, Roderick.
Yes, can you hear me?
Yes.
I'm wondering what the composition is of this dust that is able to withstand 1,000,000-degree heat.
Yeah, so this is a good question. It's probably not so different from what you would find under your bed, and probably not so many human skin cells. But it's silicates and carbon-based things. It's dust. So the 1,000,000-degree gas is really hot, but it's not very dense. And so if you are a dense little dust grain, you probably can survive, but not forever. We think that probably this dust, after it's been in the in the hot intercluster medium for a while probably is destroyed. It's probably, there's a little sputtering that happens that you probably actually get the dust grains get broken apart over time. See, because you don't have too much dust that you see in the intercluster medium, and so the picture is probably a lot of it is broken apart. Although maybe it's just spread out. Yeah, good question. Thanks.
I believe Rick Hunter had his hand up for a moment, and it went down. Rick, do you want to ask a question?
There will be a chance for later talking if people have questions. Yeah.
And I'm unmuting. There we are. Can you hear me now?
Yeah.
Okay. The question I have may have been answered before I got there, so that was a little bit late. But how does the million-degree gas achieve a temperature of 1,000,000 degrees? What is heating the gas in the galaxy cluster? I suppose that corresponds to the question of how does the corona of the sun get heated, but
well, yeah, the corona of the sun is maybe more complicated than this. It's mostly, we think, just sort of stirring of the gas by these galaxies. As galaxies fall in, they have a lot of potential energy. As they fall towards the center of the cluster, that potential energy is converted into kinetic energy, and some of that goes into sort of stirring the gas. And so that's the current picture.
Warming the gas, okay.
Yeah, it's also, it turns out, because of how hot the gas is, it's very hard for it to cool down. We think of space as being cold, but one of the problems is that there's not a good way for heat to get away from objects except by radiation. And this gas is so hot that there aren't a lot of effective ways for it to cool, which is, again, it's sort of counterintuitive because we think of space as being cold. But it's definitely it's an interesting thing. But yeah.
Well, the radiation it encounters is radiation that would contribute to its heating, and if it collides with another molecule, that molecule is probably in the same temperature distribution. So I understand that it's not going to be easy for it to cool off.
Yeah. There's not a lot of effective radiation pathways. This X-ray emission is pretty faint. So, yeah. Are there other questions before we move on?
There's one additional question from Stars and Planets, who you can unmute now.
Perfect.
So will the gas and dust that flies out of the galaxies can create another galaxy?
Probably not another galaxy. Mostly, though, because there's not enough of it. However, we do think it can create little star clusters, little regions where there are stars that are being formed. So not a galaxy, but maybe like a little mini island universe. It's not quite a galaxy, but yeah, good question. Okay, so let me go on for a little while, and we'll stop again and see if there's questions in a little while. So these galaxies apparently lose their gas in clusters. So what happens to them? Well, to get at that, I want to talk a little bit about the two general different kinds of disk galaxies that we see in the universe. And so these are so on the left is a picture of a spiral galaxy, a galaxy like our Milky Way. Spiral galaxies are disks, and they have a lot of gas and dust and stars and dark matter and all those kinds of things. But they're sort of a flattened disk. The galaxy on the right is a kind of galaxy called an S0 galaxy, or sometimes called a lenticular galaxy. They're called lenticulars because on their edges they sort of look like lenses. And lenticular is the adjective form of lens. So lens-like. But they're disk galaxies, and they have a lot of stars and dark matter, but not a lot of gas and dust. And so one of the things that was sort of realized, it has been realized for a while, and about a little over 40 years ago, one of the first sort of clear results on this is that the galaxy types are not the same everywhere in the universe. And so this is, I'm going to show a plot. I think maybe it's the only plot I show today. This is from Alan Dressler's work in 1980. Dressler in 1980. He was one of the first to show really convincingly something which, so let me explain this figure and then I'll explain what it means. So on the x-axis, on this bottom axis, is a measure of galaxy density. Basically, how tightly are galaxies packed? How much more likely are to find galaxies near one another? So on the right-hand side, this would be like galaxy clusters, lots of galaxies really close to each other. On the left-hand side would be galaxies where you don't have a lot of galaxies close to each other. And so and then on the y-axis, on the vertical axis, is the fraction of galaxies that are the different morphological types. So this blue line is the number of spiral galaxies, the number of galaxies that look like this, that have this sort of star-forming gas, dust, blue stars. We'll get to blue in a second. And in the field, in places where there aren't a lot of galaxies around, about 80% of galaxies are these spiral galaxies. And about 10%, the yellow line, about 10% are these disk galaxies that aren't forming stars, so-called S0 galaxies, lenticular galaxies. And what you see is as you go to denser and denser environments, as you go towards clusters of galaxies, you end up with fewer and fewer and fewer star-forming galaxies, fewer and fewer spiral galaxies, and more S0 galaxies. We'll ignore the red line for tonight. But the basic picture here is that in low density environments, you have a lot of spirals and not a lot of S0s. And in galaxy clusters, the opposite is true. You have a lot of S0s and not a lot of spirals. And so one of the pictures, one of the ways that one of the things that we think is happening here is that in galaxy clusters, spiral galaxies are being perhaps transformed into lenticular galaxies, into S0 galaxies. And one of the ways that can happen is from this gas stripping. So this is a sort of an interesting process to understand, how this gas stripping is happening. And so we see this happening in clusters, and we want to know, I think, sometimes a little bit more. And so there's a lot of sort of questions around how we would think about, the kinds of questions we might want to answer. And these are all questions that at one time or another have occurred to me as something we might want to try to answer. And not just me, but lots of others who study these kinds of things. And they all sort of get at the sort of the details of maybe how this happens. We see it happening in clusters. It clearly is a significant thing because it leads to large-scale galaxy transformation. But these sort of different questions, all these different questions are sort of interesting. I want to just spend the last bit tonight talking about three of them. We'll do a fourth one as a bonus at the end, but three of them. And so the three of them I want to talk about, sort of to understand how galaxies are stripped is how does gas leave galaxies? Is it stripped all at once, or does it sort of go from the outside in, as you see in some of these galaxies? Although we'll get to that in a second. How fast are they stripped? Are they stripped? Does it take 1 million years? That would be short in the lifetime of a galaxy. Does it take 10 million years? Does it take 1 billion years? Still be relatively short in the lifetime of a galaxy. But what sort of timescales are we looking at? And how fast after gas is stripped does the star formation end? And so let me so that's going to be sort of what I want to sort of spend the last section of this talk talking about. And so ideally, what I want to answer all of these questions is I want a movie. So this is not an actual movie of a gas, but this is a simulation done by Stephanie Tonneson that shows really sort of beautifully what we think happens in ram pressure stripping. So it's looping, and so I'll let you watch it a few times more. But you start with a gas disk, and then if you sort of can see, I'm not sure how well it comes out over Zoom, but there is a sort of a subtle red gradient that goes from the upper right corner to the lower left corner that's meant to represent this 1 million degree cluster gas that fills the cluster. And so this is sort of a really beautiful image that shows how the galaxy is stripped. Again, it's a simulation. We don't have this. We can't do this. And so for a few reasons. One is that we only see the gas when it's not there, once it's already, gas when it's there, not when it's stripped. But the second thing is this process takes a long time. It takes tens to hundreds of thousands of years at least. And so that is too long for us to watch. We can't watch this as it happens. And so one thing we can do is look at lots of different galaxies and look at the gas, and that's fine. But another thing we can do is we can look at the stars that are left behind. So this gas, as it's stripped out, it's just the gas that leaves the galaxies, and the stars are left behind. So the thing I would like is I'd like to be able to look at the stars that are left behind. And so why do I want to do that? Well, let me tell you, I want to tell you a little bit about stellar evolution. This is a little bit of a side track, but I think it's helpful. So when stars are formed, stars form in clusters, and stars of all sizes, big stars, little stars, medium-sized stars. They all form at once. And it turns out that most of the stars that form are relatively low mass stars that are less than the mass of the sun. And there are a few high mass stars that form, but it's mostly low mass stars. And so this is just my little illustration, meaning to show a star cluster. And there's one big, hot, massive star, a few sort of intermediate mass stars, and lots of little stars. And if we can take a census of what stars are there, that gives us a sense of how long ago this whole cluster of stars formed, because the highest mass stars, these big blue stars, which dominate the light, they're incredibly luminous. They put out a lot of light. They're blue. They live fast and they die young. They have a beautiful sort of they die in sort of beautifully spectacular ways in supernovae, but they don't live very long. And so what you can do, and there is a well-known stellar mass lifetime relation. So I said I was going to show you one plot. This is my second plot. Masses of stars. So this is on the right, on the x-axis is the mass of the stars, and on the y-axis is how long those stars live. And this blue line is approximately this relationship. So stars that are 1/10 the mass of the sun live for something like a trillion, several trillion years, whereas stars that are 100 times the mass of the sun live for less than 1 million years. So this is a sort of a way of looking at it. So if we had a stellar census, so if we have a stellar census such that this is when this is what it looks like when the stars form. If we wait a little while, the most massive stars die. They burn out. They go supernova, and so some of these stars have died. And so if we look at what the highest mass star that's still left, so this is the highest mass star that's still left, we can go back to our trusty mass lifetime relationship, and we can say, okay, well, this is the mass of the most massive star still left. And so that tells me that this whole population is this age, because this is the one that's survived, and it gives us an approximate value of how old the stellar population is. And people who study star clusters in our own galaxy do this really effectively. They make these things called HR diagrams or color magnitude diagrams that effectively is doing this. It's looking at the mass of the mass of the stars that are still alive and using that to figure out how old the star cluster is. And so that's a sort of a good way of looking at something you can do in our cluster. The challenge with what I do, extragalactic astronomy, galaxies outside of our own, is all of these star clusters are concentrated into basically one little dot, one little part of a galaxy. And so we can't look at individual stars, but we can look at the colors, and we can take advantage of the fact that hot stars are pretty blue and cool stars are relatively red. And so here are two galaxies in the Virgo cluster. These are both galaxies that have had their gas stripped. These are both images. They're not great images, but they're images from the Sloan Digital Sky Survey. I mean, they're great. They're actually really good images, but not, when you're used to looking at Hubble or James Webb images, they're not as sort of striking. But they're both of the same, taken in the same way. And one of the things that you might notice is, especially if you look at the outer disk, the place where there's not stars forming anymore, here, for example, here or here, you can notice a real difference between the colors here. And the colors are subtle. It's a subtle difference. But if you look at the one on the left, the colors are somewhat bluer, and the one on the right, the colors are somewhat redder. And by looking at the colors of these galaxies, we can learn something about when they stop forming stars. So, for example, the one on the left is bluer because its blue high mass stars are still alive, or are still there. Those blue stars still being there tells me that the population of the galaxy on the left, the light from the galaxy on the left was forming stars more recently than the stars on the right, which tells me that the one on the left has been stripped more recently than the one on the right. Colors are really useful. You can do this in a lot of different galaxies, but perhaps even better than colors is taking the light from the galaxy, not just taking sort of, does it look blue or does it look red, but taking the light from the galaxy and spreading it out into a spectrum. If you can spread it out into a spectrum, you can learn more about sort of the detailed light profiles of these galaxies. And so by making a spectrum of these galaxies, we can see we can learn some things about them. So here are some models. Again, these are theoretical models, and these are populations, stellar populations, groups of stars that are a bunch of different ages. So the one on the top are a population that stopped forming stars about 10 million years ago. This one is 50 million years ago. This is 500 million years ago, and this is 1 billion years, a gigayear. And what you will notice, what I want you to notice is the color is a little bit different, right? These are bluer and these are redder. But what I want you to notice is that the strength of these lines change with time. And so these are hydrogen absorption lines. They come from the atmospheres of stars. And I don't want to get into the details of it too much, except to just notice that in some of the populations, those lines are stronger than other lines. And they're really powerful diagnostics for how old the stars are, the stars that are left behind. One thing, one way which we've studied these galaxies is we've gone to Keck, which is one of the biggest telescopes on the surface of the planet, and taken spectroscopy of a number of galaxies in Virgo. A number of Virgo Cluster galaxies. And basically what we do is we just sample the light. So the bottom picture, we sample the light in a band across the bottom. And by looking at the light that comes from that and analyzing it, we can get a handle on how old the stars are, how recently they stopped forming stars. And that gives us some sense of when the gas was stripped. And so what do we see? So in a galaxy, in this galaxy, which is NGC 4522, we have spectra from two different places. One from sort of right here. So I have the little blue box here showing approximately where the spectra are, and one from a little bit further out, actually quite a bit further out. And without getting into the details of what the spectra show, what I want you to sort of take away from this is that these absorption lines, these things that tell you the age, they look very similar. They're about the same strength. This dip is about the same as this dip. This dip is about the same as this dip, and this dip is about the same as this dip. Those dips in the spectrum give you some sense of how old they are. And so what we see in this galaxy is that this part of the galaxy stopped forming stars at about the same time that this part of the galaxy, about at the same time, which in turn suggests that this whole part of the galaxy lost its gas sort of all at once. The gas was swept up and just shut off star formation in this outer part of the galaxy. So that's one example. That's one example. Here's another one. Here's another galaxy, NGC 4402, and I'm going to show you three spectra, all sort of on the left-hand side here. And so here's one spectrum. And so this is one very close to the place where there's still star formation going on. And what you see that these lines are all relatively strong. If we go a little bit further out, the lines get a little bit weaker. So to some extent, this one, but especially these two on the left, get a little bit weaker. And as we go even further out, the lines really start to disappear. And so what this is showing is that let me go back. Let me see, go through my old animation again. Sorry about that. what this is showing is that, far out you have relatively weak absorption lines. And that's telling you that there's an older stellar population, older group of stars, gas that was stripped longer ago. Whereas close to the center, you have younger stellar population, stronger absorption lines, younger stellar population. And so these two galaxies taken together are sort of two different ways in which we think galaxies lose their gas. This galaxy on the top, NGC 4522, seems to have lost its gas all at once. It's all sort of got swept up at once and within, all relatively similar. Whereas this one, it seems a little bit slower. Maybe actually there may have been maybe sort of multiple events that have stripped it. Different ways we can look at that. There's yet another galaxy which seems to show a population that's sort of constant in the northeast, meaning it was stripped all at once here, but sort of more slowly stripped over here. And so there's a lot of sort of details that we can get at by looking at this. So this is one. These are sort of three different examples of galaxies in Virgo, and one of the things that we sort of conclude from this work is that some galaxies, such as this top one, NGC 4522, seem consistent for being stripped all at once. You remove the gas all at one time and it all gets pushed up, whereas others show sort of extended multiple stripping events. And so these questions, these questions, which I sort of said I was going to try to address, is this question about is gas peeled back or does it all leave together? And the answer seems to be both. Both seem to happen, but you do see evidence that the gas can be relatively slowly peeled back, and it leaves galaxies in sort of a gradual way. How fast are galaxies stripped? Fast, at least by galaxy standards. Within a few 100 million years, it seems like they could be stripped. And so this is perhaps an effective way for taking a big spiral galaxy and transforming it into a disk galaxy that's not forming stars. How fast after the gas is stripped does star formation end? Almost immediately. If you look back at these galaxies, let's look back at this one. If we look back at this galaxy, we find the region right here out beyond where there's gas and dust. We find that it was forming stars very recently, within about 50 million years of now. So it stopped forming less than 50 million years ago. And so that suggests that this gas and dust left, and then almost immediately the galaxy stopped forming stars, which I think is more or less what we expect, but still good to see. So this is this. And so these are sort of the the big picture questions. But I just want to point out one thing actually, which I've already showed, is that it does appear that in this, one of the things that can happen to the stripped gas, which is you asked, was a question about earlier. One of the things that can happen in the stripped gas is you can actually form new little star clusters. Stars form in these little clouds of gas and dust that are stripped from the galaxy. So you actually get new little areas of stars that are leaving the galaxy really sort of beautifully. Just to sort of summarize briefly, I think one of the things that's interesting, and you can see by looking at galaxies like the Virgo Cluster, you can see galaxies being transformed from these sort of star-forming spirals into these quiescent disk galaxies. This is maybe one way that you could take a galaxy that looks like this and make it into a galaxy like that. It's probably not the only way. I've told you about one of the things that happens in dense environments, which is this gas stripping, the RAM pressure stripping. But there's also other things that go on, mergers and collisions and things like that. And so there's a lot of other things that can happen. But I think we've seen evidence that at least in clusters, it can be a really effective way of pulling gas out of the galaxies. And it appears when you pull the gas out that the galaxies relatively quickly stop forming stars. Which is sort of which is really cool to see in front of our faces, but using the stars that are left behind to get a sense of the timescales, I think, is also a really powerful, a really powerful thing. So that is mostly what I wanted to say. I'm happy to answer questions if people would like to talk more about this. I see some questions in the Q&A, which I'm happy to answer. But thank you for thanks for your attention. So I can move on to questions and answer now if you want.
Well, thank you. So the question that's been waiting the longest is from Bonnie, who asks, What is the dust in our galaxy doing? Is it stable, cooler?
Well, so it's doing a lot of stuff. It is definitely the case that it is a little bit more stable. But a lot of the dust probably forms in the atmospheres of dying stars. And so that dust, is sort of rejuvenated and we think can be destroyed. Definitely stable, definitely more stable, definitely cooler, but still doing interesting things. So yeah, thanks.
The next question is from Angel, who asks, this is in regard to the slide that had the bluer galaxies versus the redder galaxies. They ask, how do you take into account Doppler red-blue shift using the stellar age measuring technique based on color?
That's a great question. Let me go to the blue and red. So a few things. One is for the galaxies I study, which are relatively nearby, the amount of the Doppler effect is not going to change the overall color of the galaxies very much. So for these galaxies here, these are galaxies that are red and blue because the stars in them are red and blue. And the amount that they shift, because the Doppler shift is tiny, 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 tiny. You can see it in spectroscopy, but you can't see it in imaging. If you compare that, however, to things like this image from the James Webb Space Telescope, which is looking at galaxies a lot further away, then a lot of these galaxies, especially the ones that are sort of the ones that you can see maybe in the close-up images a little bit better, some of these really distant ones are indeed red because they are highly redshifted. It's a shift in the it's this cosmological redshift. It's not quite Doppler, but it's cosmological redshift that you're seeing here. And for these, you have to correct before you do them. So these look red. This could be a blue galaxy. This could, although James Webb is pretty far in the infrared, so it may be red. Anyway, you do have to correct. And one of the ways that you correct is by looking for these patterns, these absorption line patterns. And so these are lines from hydrogen. This is a line that is at a wavelength of 4,861 angstroms. And this is a line that's at 4,101 angstroms. And so you know what these lines should be. And so one of the things that people do when they're looking at really distant galaxies is they look for these patterns of lines and then see where they are, and then they know where they should be, and so they know how to correct. So that's one of the things that you can do for correcting for either Doppler shift or cosmological redshift. More questions.
The next question is from Philip, who asks, is it possible to utilize spectroscopy with computer modeling of dust to trace the history of how dust moves over time?
Cool. Yeah, I'm sure it is. I think, one of the things, so you can certainly use spectroscopy, although imaging on dust is also really powerful. The problem with spectroscopy is to get things like to know stuff about like how it moves. You really want to know its speed, and for that you really need Doppler shift. And you certainly can do infrared spectroscopy that will tell you how the dust is moving, the dynamics of the dust. A lot of what is done sort of in a practical way is actually looking at gas, because it's often much easier to measure the dynamics of gas. Although I imagine with Webb, there'll be a lot more work on dust and how the dust moves as well. But yeah, there's I hope one of the things that you've seen from my talk is that there is a real connection between computer modeling and observation. I think there are astronomers. I am primarily an observational astronomer. I'm interested in sort of taking data, taking spectra, or taking images, and trying to understand that. But you have to understand modeling in order to actually interpret your data for a lot of things. So yeah, thanks. Good question.
Okay, the last question we have pending is from Stan, who asks, does the direction that the galaxy is falling towards the cluster affect the rate of gas stripping? For example, a galaxy disk approaching the center of the cluster versus on edge approaching first. One edge approaching first.
Yeah, absolutely. Yeah, this is really interesting, really cool. There are galaxies galaxies, as you might imagine, galaxies that are falling towards the center of the cluster face on, they experience a wind that can really effectively push the gas out. Like these galaxies, this galaxy here and this one are probably relatively close to face on. They both are sort of falling towards the cluster, and they're experiencing the wind that's pushing the dust out. This other one I showed, let me see if I can get a good image. 4230. Here, 4230. This one is one that we think is probably not falling quite face on. And so one of the things that you see is that we think this edge is experiencing a lot of the pressure, and the dust and gas and stuff that's in the galaxy is shielding a lot of the rest of the disk from that wind. So that wind is, it's like in a wind shadow almost. And so you have the wind is sort of is a little bit steeper here. And that's probably why this side has a lot of stuff still left, and it's a much slower stripping process. So yeah, absolutely. We can see in detail that happens. But one of the things that happens as these galaxies fall into the cluster is that they tend to sort of experience force from all different directions as they move on their orbit through the cluster. And for whatever period they're experiencing the sort of the face-on wind, that's when they're probably most likely to actually be stripped and lose their gas. So yeah, thanks for that. More questions? You can raise your hand if you want to, or put it in the Q&A if you want. Okay, so I see I can see the Q&A now, so I'll read on. Do active galactic nuclei shift the stellar formation rates enough to help model the effects of ram pressure? Yeah, so active galactic nuclei, for those of you who don't know, are big black holes. Well, all galaxies have big black holes in the center. Active galactic nuclei are big black holes that are eating right now, or are feeding, gas is flowing on, and they're often are big outflows from the center. The interaction between active galactic nuclei and ram pressure in clusters is really interesting, because as you might imagine, if you have a big thing in the center of your galaxy that's sort of shining and a big powerful jets and things that are coming out of it, that can also affect star formation. That can also actually push gas out of the galaxies. And so one of the questions that sort of people have been trying to understand for a long time is how does AGN activity, how does active galactic nuclei activity affect star formation rates versus things like ram pressure in galaxies, in galaxy clusters? And I don't think really know. It's complicated. I actually was just talking to someone who studies AGN in galaxy clusters, and we were talking through this. And there's sort of two things that can happen. One possibility is as these galaxies fall into clusters, the gas gets disturbed, and that drives the gas towards the center of the galaxies, which effectively turns on AGN, can make the AGN stronger. But then there's also the question that if an AGN is shining in a galaxy, that can sort of puff up the gas and make the gas easier to strip. And I don't think we exactly know. One of the things that does appear to be true is that in most galaxies with AGN, it really only affects the center part of the galaxy. And so the sort of global effects that we're talking about with ram pressure are probably more likely to affect sort of the whole galaxy. Whereas the sort of the central, the central really bright black hole is really a big deal for the center part of the galaxy, but less important for the outskirts that can be sort of effectively shielded from the AGN. Yeah, it's a good question. More questions? Everyone's seen the pictures of Webb. If you haven't seen the pictures of Webb, see the pictures from Webb. I showed some of them in my slide today, but go and look at them. Not just I couldn't figure out a way to put the planetary nebula in my talk. Otherwise I would have. That's also amazing images. So anyway, you're quite welcome. Quite welcome. Thanks everyone for coming. If there's nothing else, that's it for tonight.
Actually, if I may jump in, Rick Hunter
please.
has one more question, so I'm going to allow him to speak.
Wonderful. Yes.
Is deeply offended.
There is a picture of Stephan's quintet among the web pictures, and that's a group of interacting galaxies that may be ramming gas out of each other. In fact, it looks like they are. And I wondered if you could, first of all, show a nice large version of that on your screen, and second of all, could you discuss it with reference to what your talk was about?
Absolutely. So yeah, let me pull up. Actually, I thought this might happen. So let me. Okay, here we go. Let's see if we can make a better image. So this is Stephan's quintet, which is a. People can see Stephan's quintet. Yeah. Okay. This is a really sort of a beautiful image. So Stephan's quintet is a really interesting group. So this is what's called a compact group of galaxies. This is something different is happening here than is happening in big galaxy clusters like Virgo. These are galaxies that are gravitationally interacting with one another. And so this is a case where, oh, sorry, I didn't mean to minimize it. This is a case where, let's see if I make, okay, there we go. This is a case where you have sort of a really sort of beautiful example of the dust, which is dust and gas shown here, but also the stars. The stars are also sort of extending out here, and so what you actually see here is is sort of this really sort of beautiful tail structure. So these are galaxies. One of the things that can happen in galaxy clusters is the ram pressure stripping I've talked about. This is a case where these are galaxies that are sort of gravitationally interacting, galaxies that are probably merging. And so this is not just affecting the gas. This isn't putting the gas. This is actually pulling already formed stars out of the galaxies as well. And these kinds of things happen in clusters, but not as frequently because the galaxies are moving too fast. But these sorts of compact groups are, this is another way of this is yet another way that galaxies can interact and can change, and actually is probably explains. I skipped over when I was talking about galaxies. I talked about S-zeros, lenticulars. I talked about spirals. I didn't talk so much about elliptical galaxies. These big sort of masses of stars. These are probably, not for sure, but probably the result of mergers. These are probably the result of galaxies that merge together. And so it is likely that a kind of interaction like you see in Stephan's quintet could form one or more of these elliptical galaxies over time. Anyway, thanks for that. Yeah, no, I'm happy to spend all the time talking about the web images. And well, since I have you here, I will just show the other. This is a great, really cool spectrum, but this is this amazing planetary nebula image from Webb, which just again goes to show the range of things that we're going to see with it. I just finished teaching a class this last term on life in the universe, and I'm really enthusiastic for what Webb is going to be able to tell us about planets around other stars, which is again totally different from my research, but still totally fascinating and totally cool. So.
Hey, I see no further questions. So going once, going twice.
Thanks so much to everyone for hosting me tonight. It was really fun.
All right, so we're going to wrap up the webinar for tonight then. Thank you very much for that presentation. If I can speak for myself, I learned things that I want to bring back to my own students now. I didn't even know that gas stripping was a thing before today. So that's awesome. So if for our attendees, if you'd like to re-listen to parts of this, or if you know somebody who missed it, we are going to be posting the recording in the next week or 3, so please keep an eye out for that. As you exit, you're going to be prompted to fill out a survey. It would be a great help to us if you could take a minute to provide us some feedback on the talk, about what you'd like to see for future talks, and about how you heard about this. And thank you again, Dr. Cowell, and I just want to thank everybody else for their attention tonight. Good night.